Hey guys, welcome back to inequality topic. In here we are going to consider linear inequalities with several variables. To be precise, we're going to consider two variables, x and y, and we are going to consider how they can form the whole regions on Cartesian plane, or basically on xy set. Let's consider first an equation, x equals, let's say, 2. What you can see here, so you can see that just one single, the value for x is already determined, x equals 2. But graphically, what it means if you set up this equation on Cartesian plane, so indeed you'll have the set of points, or LOCI, what is called Loci, right? You remember it from previous studies, so LOCI, basically set of points that satisfy x coordinates of those points should be equal to 2. Y coordinates can be any. So if you set up that on Cartesian planes, you'll get that vertical line that goes through the value x equals 3. So that's the value of those points when x, y is x equals 3, x equals 2, of course. So we set up the line that goes vertically through the value x equals 2, okay? So you understand that any point taken on that line will satisfy the equation x equals 2, because no matter what stays for y, right, x coordinates is always fixed and 2. So you can take random point x, capital X, so that the coordinate for x is going to be 2, but y is some coordinate, which is in this case 1, 2, 3, 4, 5, right? Yeah, so y equals 5 at this level. However, if you consider inequality, so that means for that, LOCI is just simply any points on that line, on that vertical line with the equation x equals 2. However, if you consider inequality, let's say x strictly more than 2. In this case, you can see how inequality will form not the line, but the region. So, and region is going to be here. So any point with any y coordinates, but with x coordinate more than 2, so that x more than 2 will form the region that satisfy our inequality x more than 2. So we put R, capital R stays for the region. So if you want, I can even highlight that region. So use, let's say, green. And I can highlight that region simply onto the right of our line. As you can see here, the region looks like the semi or half the plane, right? That actually with x values more than 2. So coming back to our inequality, so any point with x more than 2 and any y value will satisfy our inequality and hence form the region that we call wanted region or desirable region R. Okay, in this case we also can form the region by using several inequalities, or even like several inequalities and several equations. So no problem, we can form that. So I can set up that's here, so just go a little that way. Okay, so let's form region R by setting up several inequalities. So let's first consider y equals 3 and also consider x equals to recently that we discussed. In this case, if we want to see how the region R will be formed, we just simply set up x, y set, and we need to set up two lines. First, the vertical line that goes through x equals 2, as in the previous case. It's here. And y equals 3. So the horizontal line that will go through the value y equals 3. Okay, so in this case, we have intersection of LOC, right? So basically two lines, and because that the system, basically we need to satisfy both, that will be the single point here. However, if we convert those equations into inequality, we can say that instead of single point that satisfies both, basically both equations, in this case we have inequalities. Let's say y more than 3, so that's the level y equals 3, and that's x equals 2, and let's say x more than 2, we'll have the region. So first of all, any point with any y satisfying inequality x more than 2 is the region simply here, just on the right side of x equals 2. So that's the region simply here. Okay, I'm not going to highlight, so instead of like in previous case I highlighted the wanted region, in this case I highlight the region that we are not satisfied. Okay, so I use the marker highlighter and put, let's say, I don't know, let's take blue one, and I put the region that we are not satisfied with. So that's, let's say, blue highlighted region doesn't satisfy my inequality x more than 2. So that's why the region that we want to have is simply any point with x coordinate more than 2. Okay, basically that one. What about y more than 3? Y more than 3. I want to highlight again the region that doesn't satisfy condition for y. So basically it's just below the line, right? It's just basically below the line y equals 3. So that's why I highlight the region that's strictly below the line y equals 3. So what we left with? Let's have a look. We left with the region here that any point from that should have the coordinates x more than 2 and y coordinates more than 3. So any point from the region that's not shaded right now is going to be wanted coordinate. And conditions for the coordinates satisfy or set up by this system of inequalities. That's how we can find the whole region, and that's how the system of inequalities will form the region, okay, in this case. So, and that's the typical way how to understand what's the wanted region that satisfy the system of inequalities. Basically, you need to shade all unwanted parts, and what you're left with the region that satisfy your inequality. Yeah, your inequalities. However, you see that inequality is strict. In this case, I use the red dash line. Probably, yeah, it's better to use dash line. So here, in order to indicate that we have dashed boundaries. So that means that on boundaries, we cannot take the values on it. because the inequalities are strict, so boundaries are not eligible to be the points. So that's why the region actually we're interested in is that one. So strictly above y equals 3 and strictly more than x equals 2. Okay, that's the region. So, and we can set up the letter R that stays for the region that we are looking for. Okay, this is the way. But how to be with like several inequalities. Let's say we're limited with several restrictions for x and several restrictions for y. So in this case, we simply can do the following. So we can say that we've got, let's say, sort of constraints that we put on x value, let's say from 0 to 3. It's not just one inequality, it's two. Actually, you can consider as x more or equal than 0 and means in union with x less or equals to 3. So actually we have the range for x so that any x eligible for our inequality within 0 and 3. So within this range. And for y, let's say we also have conditions. So from 0, let's say to 2. Okay? That we can also consider as two inequalities, y more or equal than 0 and y less or equal than 2. So if we put it on Cartesian plane, so we should get something similar to that. Okay, that's Cartesian plane. So we set up y, we set up x, and we set up basically two lines. The first for x, boundary, x equals 0. That's the boundary line. So it's here, that's the vertical line, and x equals 3. So 0 and 3, and we put two vertical lines. In this case, I'm not going to use dashed lines, so I put normal lines because we have non-strict inequalities. So I simply put the vertical line here and the vertical line here. So that's why unwanted region, I'm going to shade unwanted region right now, relating to x values as simply that one. So here we are not satisfied if we take any points from that blue region, and also here. Okay, so that's why we stays with this bar within the range for x from 0 to 3. Okay, so next one, what about y conditions? So for y conditions, we have the boundaries y equals 0 and y equals 2. So y equals 0 is that line or that level. So that's why we're going to use that level. And another level, y equals 2. It's here. So we have y equals 2. And here is y equals 0. By the way, I can set up also for x. Okay. So now, relating to y conditions, we're satisfied for any points that have coordinates for y within 0 and 2. So it means within that basically bar that's now is horizontal, or this stripe. So that's why I use, let's say, another color for the marker, let's say pink one, and trying to shade unwanted region again, so that finally we actually have the region that is not shaded, and that's which satisfy our both conditions for x and for y. Okay, so that's why for y we're not satisfied with that part of Cartesian planes and that part a little below. Okay, that part we're not satisfied. And finally, where's our region that we left with unshaded part? It's here, right? So any point within that range, so within this actually rectangle, will satisfy any point from that region, will satisfy our system of inequality right there. So if you take any point to check, for example, that point, it will have the coordinates x equals 2 and y equals 1, so it will satisfy, because if you plug and try to test, it will work. Okay? So I hope you got it, how it works for like those simple inequalities. And now let's consider a bit more complicated case. So when you have several variables in one inequality, let's try to do that. However, we'll be applying the same strategy here. Okay, so let's set up inequality in the way 3x, let's say, minus 4y. In this case, we're going to consider the right side non-zero, like some number. Let's take a very convenient one. Let's take probably 12. That's a good one. And let's consider which region in this case is going to be satisfy our inequality. So what I recommend to do, because here you can plot the line with general equation 3x minus 4y equals 12. So to plot that, you need to have 2 points. So that's why we simply say that, okay, let's first find y-intercept. So we plug x equals 0, and from where we can find that y is negative 3. And also we can plug y equals 0 in order to find x-intercept. So that's the y-intercept. And if we plug y equals 0, we'll get x-intercept from where it's 4. Okay? So we've got 2 points, x and y-intercepts, and we can drop them on Cartesian plane. So it's here. So y, x, and let's drop the points. So I use the red one. 0, when x 0, we have negative 3, it's here. So that's negative 3, it's y-intercept, and it's 1 point. And the second point, 4 and 0, which is actually here. So that's another x-intercept. Okay, so we use the straight line and drop it right here. Okay. Not so cool. So that's why I'm going to use that one. Yeah, it's much better. All right, so we've got the line, which is in this case is the line with the equation, general equation 3x minus 4y equals 12. Okay, so we've got that. But now we are going to understand which region we satisfy with. Okay, in this case, the line is an infinite, right? And that means it will split the whole Cartesian plane on 2 half of planes. So the top one, which is above your line, and the other part, which is below. Basically, we have semi-planes, 2 semi-planes, and one region which is above the line and one region is below. How to test which points? Actually, we have only 2 choices, below or above. And now we need to decide which region we satisfy. Region 1, which is actually above, or region 2, which is below that line. So that's our line with the equation 3x minus 4y equals 12. Okay, so do we need to choose R1 or R2? How to judge, how to choose that, which region satisfy for our inequality? Actually, you can plug any point, any very convenient point from region 1 and region 2. And if we got the right inequality, that means that this point and the set of points from the region we chosen actually satisfy our inequality. So let's take any point. I bet that this point, the origin with coordinates 0, 0 from region 1, will the best one. So that's why I test any random point from region 1 and we plug 0, 0 into our inequality. So we've got 0 more than 12 if we plug x and y coordinates instead of x and y values into inequality. So that's incorrect, right? Incorrect. So that's why region 1 doesn't satisfy our inequality. So that's why we just can shade this region and say, okay, use the blue one, so and say that this doesn't work. Basically, this region and any point from that region doesn't satisfy our inequality. So that's why the desirable or wanted region is region 2. So that's why we can say that the solution is any point from region 2. Basically satisfy our inequality. So we can say that region 2, so that any point with x, y from region 2 satisfy inequality 3x minus 4y more than 12. However, look guys, we have strict inequality. That means the boundary that is here, so that's the boundary, will actually correspond to the equation 3x minus 4y equals 12. We are not eligible to include in region 2. So that's why instead of that line, we're going to use dashed line, not the solid line, but dashed line, because we're going to exclude the boundary. So that's why region 2 graphically represented by the area below the dashed line. So the boundary is not included. Okay? If it were non-strict, like more or equal to 12, so we will use our solid line and we will include the boundary. Okay, so that how it works for single inequality with two variables. You understand that it's linear one, it's not quadratic, it's not like polynomial. So we've got standard linear dependency of x and y, and in inequality they compare it with some number, so that's why it's linear expression on the left hand side, and they compare it with some number. And this is the way how we can determine. There is also other way how we can actually determine the regions that satisfy. Right now I'm going to show you. So for the same inequality, I can show you how we can do in different way. You remember that this is the general form of the line, right? Because the left hand side is linear expression, so this is the general equation of the line. However, we can figure out the equation of the line in the gradient intercept form. So if we use gradient intercept form, we need to arrive to that one. And in this case, we can easily, without any plugin, like how we tested before, we can determine immediately where our wanted region. So in this case, we need to come to gradient intercept form from the general one. So I'll rewrite, so 3x minus 4y more than 12. And your final way how you need to arrive to gradient intercept form of the line is to say that we need to leave y alone, so that it can be more, or let's say it can be less, and something some expression with x involved in x will be on the right side of our inequalities. So in this case, because we're going to stay along with y, and right now we have negative 4y, it's better to transfer negative 4y to the right side of an inequality. And hence, after transferring, we'll get the following. 3x, so 12 transferred here to the left side. And we keep the sign, inequality sign, the same. That's simply the same strategy as we applied for normal inequalities with one variable during our solution process. So 3x minus 12 is more than 4y, from where now easily we can divide by 4. Not afraid, and then we need to swap the signs. In this case, in this strategy, we keep the sign, inequality sign, the same. So if we divide both parts by 4, we've got 3 over 4x minus 3, more than y. But right now you need to rewrite so that it will be clear how y value compared with the equation of the line. Okay, so any y less, strictly less than those values determined by equation of the line, 3 over 4x minus 3, will be satisfy our inequality. So, and indeed, so actually if you set up y of the line, which is 3 over 4x minus 3, so it's actually here what's drawn on the graph already. So this is the general form, however this is y-intercept form. Why you need y-intercept? Because from the y-intercept, so from gradient intercept form, you can compare your y with your equation of the line. So that's your equation. So you can, if you're not sure, you can set up the line using the previous method, x equals 0, so just by finding two values by setting up the value tables for the line. Or you can use the gradient intercept form in order to find, okay, that's y-intercept, it's easier, right? And gradient 3 over 4, or you can find another point. So it doesn't matter. But the crucial thing here is you have any y compared with y of your lines. So in this case, you clearly see that any y point below your line, so if you fix x, let's say you fix x here, okay, in this case 1, 2, 3, 4, oh, it was transferred, it's weird actually. Okay, so anyway, if you like fixed x and say, okay, your x, let's say in this case it's 8, looks like so, right? So you put x equals 8 and you're looking for y value, it's here. So you plug into the equation. So when x equals 8, you understand that the equation of the line will give you y value equals to, according to the line, so you'll get 8 times 3 over 4, which is actually 6, and 6 minus 3 is 3. So you'll get this level to be 3. So that level to be 3. However, you understand that your y for that value is any below 3. So you'll get the equation, inequality, y below 3, y is less than 3 means any y for x equals 8, any y coordinates below y equals 3 level will satisfy your inequality. That means for the whole region, so for any x, you should have y less than the y of your line. Okay, so that's probably approach maybe a bit trickier from the first glance, but it will give your advantages when you solve several inequalities and trying to establish the region for several inequalities in a row. Okay, so I hope this concept is clear for you, at least how to choose the region for one inequality. one linear inequality, how to find this region, you can use both methods. So the first method, which is connected with the plug-in and testing region, plug in any point from region 1, region 2, and then compare whether it satisfies your inequality or not, or using the gradient intercept form so that you understand that any y below your line satisfy your inequality, and that means graphically it means that any point below the line, right, below the line that you dropped here. Okay, so that how it works. And in the next video I'll show you how to cope with several inequalities to find your wanted region, and probably we'll also try to solve the inverse problem when you set up the region, and from the region set up by like visual by graphs, you need to set up the inequality or the system of inequalities which satisfy your region that you see graphically. Okay, that's an inverse problem. So we'll be practicing with several inequalities in the next video. Hope you like that. Don't forget to subscribe, guys. That was Daniel Dallas. See you later.